So once again, what's the positive side, or what's the advantage of bootstrapping methods? The advantage is, or the advantages are that they perform very well, even if the residual distribution, or this epsilon, this innovation process, is not normally distributed, even if it's theta-tailed distributed, let's say a t-distribution with 5 degrees of freedom, or a skewed, like the chi-square distribution with 2 degrees of freedom. Bootstrapping tests tend to perform very well and decrease the size distortion. What's the problem with bootstrapping tests? Well, the problem is that you have to have an idea about the dependency structure in the data. Because in setting up the test statistic lambda hat, we have to have an idea about what kind of dependency structure we have in the data. Yeah? We need that for, first of all, for setting up the test statistic, and also for setting up the right resampling method for resampling the residuals. So these are the major concerns. So then we have proposed in the literature, in a recent paper, a new methodology, which is also based upon bootstrapping, but which is slightly different in the approach. So what is the main idea? So first of all, we have to assume, or we would like to assume, that the expectation of our residuals, of our vector of errors u, given our regressor matrix x is 0. So we assume again strict exogeneity. Yeah? Moreover, what we know from our previous lectures is that according to our OLS estimator, we know that our beta hat, given by x transposed x inverted, x transposed y, if we take the expectation of beta hat, given this formula, is beta, which means that our point estimator is unbiased, given that our residual vector and our regressor matrix are uncorrelated. So given that our OLS estimator is unbiased, what does that mean? So it means that we do not have to have any assumption about the distribution of the residuals. The only assumption is that the expectation of the residuals of our errors is 0. That's the only assumption. We do not have to have the assumption that the process is fat-tailed or thin-tailed or slightly skewed, but the only requirement is that they are on expectation 0. So given this feature, this nice feature of our OLS estimator, we have employed this in order to set up a bootstrapping scheme. And the idea of that bootstrapping methodology is also taken from the book from Godfrey. But we will come back to that a little bit later. So how do we proceed? So this is basically the only assumption, that our point estimator is unbiased. So how does this bootstrapping scheme that we have introduced, how does it work? Well, we can define a matrix. We can put the vector of our dependent variable y and our regressor matrix x. We can put it into a matrix. Let's call this matrix W. And if this is our model here, then our W is defined as y1, y2, y3, and so on. It's simply the vector of dependent variables, and then in the next column, we have x1t, or it's x11, x12, x13 until x1t. And here the next column vector in our matrix W is then obviously x21, x22, x23, and the last is x2t. Then the next column vector is x31, x32, x33, and so on until x3t, and the last one is then x41, x42, x43, and finally x4 capital T. That's the we basically just plug the vector of dependent variable vector and our regressor matrix into a common matrix and denote it as W. That's it. So here we have the first column vector is our independent variable, and here the column vectors 2 until 5. These are the corresponding regressors in our model. So then what we do then is we do something from small b is equal to 1 until capital B. Again, we do something capital B times, and let's say we do something 1,000 times. So we draw n blocks from our matrix W. We draw n blocks from W, from this matrix here, and we put it into a new matrix, and we call this matrix WB. So the block length of the first block that we draw from W has the length of, let's say it has the length of h. And this block length h is drawn randomly. And this it follows a geometric distribution. H follows a geometric distribution, and the geometric distribution is defined by one parameter, and that's P. P is the probability of success. So what is a geometric distribution? So it gives us the number of failures, how many failures did we have until success occurs. That is important now to bear in mind. So the geometric distribution gives us the number of failures until success occurs. So let's say x is 0. Well, what does it mean? If x is 0, it means there were no failures and we had success on the first trial. So what does it mean? So it means if p is the probability of success, the probability of failure is 1 minus p, right? So it's 1 minus p to the power of 0 times p. 1 minus p to the power of 0, that's 1. That's 1. So what comes out is p. It's simply the probability of success. So what is the probability of having 3 failures? X is equal to 3. 3 failures until success occurs. Well, it is obviously 1 minus p to the power of 3 times p. And in the same way, we can compound any other number of failures until success occurs. So that's how the geometric distribution works. And the expectation of the geometric distribution is defined as the expectation of x is defined as 1 minus p over p. So that's that's the idea. So, and we will come back soon. We will discuss soon for why we set it up like that. So, but the major idea is, okay, the block length h follows a geometric distribution. So, and the feature of the geometric distribution is that let's say we have an expected block length h, yeah, and this can be any number. Let's say it's 10 or something. Then the probability that we have blocks that are smaller than h, yeah, is obviously much larger than having blocks that are longer than h. Yeah? So we have a higher likelihood of having shorter blocks, given our expected block length is h, than having blocks that are much longer than our expected or our desired block length h. So that's the core of choosing a random block length h that follows a geometric distribution. Yeah? This is a nice feature, and we'll come back to that soon for why we do that. It's obviously also possible to choose other distributions, but this distribution, the geometric distribution, has been proposed in the earlier literature. So, and again, we say that our not only the x is defined by this. In our case, we want to have the block length, our expected block length, defined as the expectation of the geometric distribution. So because of this, because we know that, we can also define what needs the probability to be. So what kind of geometric distribution do we have to choose if we want to have an expected block length of h? Now, that has the same expectation of the geometric distribution. So what we can do is then, okay, if we know that, we know also that the expectation of h times p is 1 minus p. So what we can do then is we can bring this on the left-hand side. We have then the expectation from hp plus p is equal to 1. Now we can multiply. We can basically put p outside the parentheses. And what we have left here is then the expectation from h plus 1 in parentheses, and here we have 1 on this side. So what we then get here, what follows, is that the corresponding probability that we have to choose for the corresponding geometric distribution is then defined as 1 over the expectation from the chosen block length h plus 1. Yeah. So now we know how we can translate the expected block length h that we want to have, for choosing a block length from our matrix V. We can now translate it into the probability of the corresponding geometric distribution. Let's take this away. So now we know which geometric distribution, and this is obviously, if we code it, then we know, of course, this distribution for our implementing our bootstrap scheme. This expected block length doesn't change. Yeah. So let's say in the first iteration, our chosen block length, let's say we want to have a block length of 10. Yeah? We compound the corresponding probability for the geometric distribution, okay? And let's say in the first draw n, yeah, in the first draw n, we get an expected, or we get a block length of 7. So what does that mean? So it means if this is t, that's a t by 5 matrix, right? So we have obviously, yeah. Now the question arises: which block length that has 7 row observations, yeah, should we grab of this matrix W? Yeah. So what we do is, okay, there are obviously many different possibilities. Yeah. It can be the first 7 observations. Yeah. It can be observations 1 to 7 from that matrix, row 1 to 7 from matrix W. It could also be row 2 to 8 or row 100 to 107. Yeah. So this is always, they have always 7 observations. So the question is, okay, which of these rows we should grab? And here, what we do then is, okay, once we have determined the block length and say it's 7, we we randomly choose a block length that has 7 rows from that matrix W. Yeah. So we employ a random number generator, choose randomly here a block from W that has 7 rows, and all 5 columns. This is what we do. Then we choose this. We use this randomly chosen block with block length 7 and put it here. Yeah. Then the algorithm goes back here. Then n is 2. This was the first draw. Then n is 2. And again, we employ the geometric distribution, yeah, and choose the block length randomly. And let's say in the second run, given we have an expected block length 10, in the second run, our geometric distribution gives us a random block length of 3. Then again, we go back to our matrix W. Yeah, we have different possibilities to choose 3 rows of this matrix here. Yeah. It can be row 1 to 3, it can be row 100 to 103, or 200 to 203, depending on how many observations we have, obviously. And again, we choose randomly. Yeah, we again employ a random number generator and draw randomly a block length that has 3 rows from our matrix W and put it then here below and create by this a new matrix WB. Yeah? And then again, now our n is 3. Yeah? Now we have the third draw. Again, we employ the geometric distribution, giving us a random block length. Then maybe it says, okay, the block length should be 20. Again, then we have to choose a random block length that has 20 rows from W, and of course we take all columns here, 20 rows and all columns, and we employ a random number generator that gives us randomly from this matrix W 20 consecutive rows. We grab this and paste it in here. Yeah. So we do that certain amount of times, and probably the way how we code it will exceed the length of capital T. And what we do then is we simply cut off all observations here, that are larger than T. We just cut them off. and go with the dimension that has the same dimension of our original matrix. Yeah? So, and what we get then is our first simulated matrix W1. So in the same manner, we can construct many of these matrices. Yeah? We do this, as we said here, we do this capital B times. We get capital B different matrices WB, yeah, that are WB that are basically constructed using always different blocks from our original data matrix W. So why do we choose this approach? Why do we choose a random block length that follows a geometric distribution? Yeah? Let us discuss this first. So let's say that our original data process has some sort of that one of these variables here has a sort of autocorrelation structure going on. So let's say that that's a process that looks a little bit like this. Yeah. So what happens? What would happen if we chose always a constant block length? What would then happen? Let's say we choose a constant block length h, and the first block would be, let's say, here. The first block that we chose would be this guy here. Yeah? We grab this guy and put it in our new data matrix. Let's say then we grab another random block length that has the same length, and it could be that in the next iteration we would grab maybe a block from here that has the same block length. Yeah? Let's say that's the block that we would grab. So if we would paste this block here behind this guy here, what would happen? We would have this process, right? So, and that's the problem here. So if we do not use a random block length, but if we choose always a constant block length, it could be that we have here a process that is not stationary. Yeah? That has all of a sudden that has a weird behavior that all of a sudden has this bumps here. Yeah? So that's a problem if we have always the same block length. So if we have this sort of autocorrelation structure in the data and we do not know that beforehand, so if we have sort of this kind of dependency structure and we chose not to use a random block length that followed a geometric distribution, but we would choose using the same block length for all blocks, it could be that we have a process that is not stationary anymore. So what would happen? What happens instead if we have a random block length? Let's consider this case here as well. Let's just remove this. So let's say we choose now to select the block length randomly, and again, let's say we have the same process. Let's say the first random block length. First of all, the likelihood is higher that we have shorter blocks, right? We already talked about that. And let's say the first block that we choose randomly is again maybe the first block here. put it here in the simulated series. So we choose this first guy here. And now, because it's more likely to have a shorter block, and let's say now we have randomly this guy here. So the second block is now pasted here, which looks like this. And the third block is probably also a shorter one. It's maybe this guy here. So the third boy goes here, and then we have maybe again a little bit longer block. This is maybe this guy here, which is pasted then also here. So we see using this random block length bootstrap that has more shorter blocks than longer blocks, it ensures that this data series, this artificial data series, or this synthetic data series is stationary. That is the purpose of using the geometric distribution. So what else do we need to know? So obviously, in constructing our data matrices, our artificial or synthetic data series or data matrices WB, we have to have small n draws, and we have to ensure that n times the expected block length h, that this is larger or equal to capital T, right? But what we do what I have coded, so we chose a very large small n, to ensure that our data series is always our simulated data series is always much larger, because this makes things easier, because we don't have to be concerned that we have maybe in one trial where we have a very large number of very short blocks, that our constructed data matrix is smaller than capital T. So if we chose this very large, we will not have the situation that this is smaller than capital T. So this is what we will see later on when we go through the code in MATLAB. So the only thing that we have to do is we just have to cut it here. We just have to cut the excess observations that are larger than capital T away, and that's it. So that's not any problem. So what is then the next step in our procedure? So again, now we have to have in mind, we have capital B, let's say 1,000 of these artificial data matrices WB, right? So what we can do is, so we use this data matrix, and each simulated data matrix, and we get capital B point estimator, right? So we can, for each simulated data set, we get a different point estimator. So we can plug them into a big matrix. So in our model here, our point estimator, beta hat B1, is a 4x1 vector. Then we have the next one, and then when B is here, so here small b is 1. In the next run, small b is 2. Then we get here another point estimator, beta hat 2, and so on and so forth. And in the last run, when small b is equal to capital B, which is 1,000, for instance, then we have here our 1,000th point estimator, beta hat. So what we get is, in essence, we get a 4x1,000, or in more general, a 4x B matrix of point estimator beta hat. yeah, using our simulated data matrices. So, and what is it? How does it look like? Well, yeah, we know we have here the alpha. So we have here the alpha 1, the alpha 1 1 basically, the beta hat, the alpha hat 1 1, beta hat 1 1, and so on. And here in the last row we have the beta 3 for the first run. Then we have here for the second run we have the alpha hat 1 2. We have the beta 1 for the run 2 hat, and here the last element is the beta hat 4 for the second run, yeah, and so on. The last element here is obviously the alpha hat for the capital Bth run. The second element is the beta 1 for the capital B run, and the last element in this matrix, in this parameter matrix, is the beta hat 3 for the capital B run, yeah, and this should be here a 3, of course, because we have only 3 beta parameters to estimate. And here we can also take the 1 away, because we have only one alpha, obviously. So it's the alpha for the run, for the first run. Here's the alpha for the second run, yeah, corresponding to that parameter estimate. And here the last one is the alpha hat for the capital B run. Yeah. So what we can do then is, so once we have stacked our parameter estimators into a matrix, and we know now how the matrix looks like, it's very simple. So what we can do is we can compound the variance. Yeah, we can take the variance of our point estimators in the first row, knowing that here we have all the alphas for all our simulated data series. Yeah, we can take the sample average simply, and that's the variance. That's the variance of our alpha hat. Yeah. In the same manner, we can take the covariance between the first row and the second row, and it gives us the covariance between alpha and beta 1. Yeah. The covariance of alpha hat and beta hat 1. And in the same manner, we can also estimate all of the other guys in our covariance matrix. Yeah, obviously, the second element on the main diagonal would be then the variance of our beta hat 1. Yeah, the variance of our beta hat 1. And so on and so forth. The last element on the main diagonal is obviously the variance of our beta hat 3. Yeah, and all the other elements here in the matrix are straightforward, right? So what we get is a 4x4 covariance matrix, yeah, that is based on our estimates using the simulated data series. Yeah. So what we get here, this is basically sort of the asymptotic covariance matrix. Now, we have already recognized from our lectures that the main problem in all of these tests is obviously the covariance matrix. Because if we have dependency structures in the data, the covariance matrix is always different. But what we have done is, we have used the original data set, and we have constructed a lot of combinatoric permutations and constructed many different data series that account for various dependency structures that are all based upon the original data series. Yeah? So we have a lot of different possible dependency structures accounted for, and all of them are a part of our point estimators here. Yeah? But if we have a very large sample, yeah, capital B, and now we have obviously in our modern society we have a lot of computational power. Yeah, we can also use 100,000 or 1 million of samples. Yeah, that doesn't matter. There are actually no real limits. So what we get is the limiting the asymptotic covariance matrix. Yeah, given we have a very large number of artificial samples. So that's sort of the real covariance matrix given that data. So using this covariance matrix here, let's define this covariance matrix here as C hat. Yeah? This is our C hat. Yeah? Let's take this away. We know now how to compound our covariance matrix. This is sort of the, you can see it as the bootstrapped covariance matrix. So we know that our lambda hat, our test statistic, let's call it now lambda star, is then given by R, capital R, times beta hat, which is based upon the actual data. Okay, this guy here, based upon the actual data matrix, minus small r, that guy is transposed, times what? Times capital R, we know this already, we have done this many times in this course, times C hat. C hat is now the covariance matrix that we have basically bootstrapped. Yeah, this is our bootstrapped covariance matrix, C hat, times R, capital R transposed, inverted. We always remember that this expression here is inverted, times capital R times beta hat minus R. So that's the way how we would implement our bootstrapped test statistic. Yeah? And now recall now, this is important to remember that this guy here, this beta hat, that's the estimate based upon the actual data, whereas our covariance matrix C hat, that's based upon the simulated data. So, and what we can also do is, yeah, we can also get, because this is what we already discussed now many times. So this guy here, the C, that's the covariance matrix, and we can also it gives us also at the same time the T statistics, the bootstrapped T statistics. So the bootstrapped T statistic for, let's say, alpha would be, okay, we would basically go to our actual point estimator, this beta hat, having the actual data, we get our alpha hat, our beta hat 1, and so on, and our beta hat 3. So we would grab this guy, the first element, which is our estimated alpha hat, and we would divide it by the square root of what is here, the first element on the main diagonal, because we know the first element on the main diagonal of C hat, that's the bootstrapped variance of our alpha hat, right? So the bootstrapped T statistic would be then take the original alpha hat from the actual data and divide it by the square root of the first element on the main diagonal of that guy. Yeah, very simple. And in the same manner, we would estimate the T statistic for beta 1, 2, and 3. Yeah, we would grab for the original beta hat parameter vector, the corresponding element, and divide it by the square root of the corresponding element here from our C hat matrix. So what's the important issue here? So the important issue is that for all of these data here, for our data vectors, yt, x1, x1, x2, and x3, the kurtosis must exist. Yeah? Because if the kurtosis, which is the first moment, if the kurtosis does not exist, our covariance matrix cannot converge. Yeah? We have discussed about this earlier. So the kurtosis must exist so that our covariance matrix converge to what it is. So obviously, so the this bootstrapping procedure, this one here that we discussed here, that we will also soon investigate in a computer program which is called MATLAB, and also the bootstrapping approach that we discussed before. Yeah, both are of course similar in the sense that they are data driven. Yeah. The earlier bootstrap approach, which is, let's say, the classical or the more traditional, requires that you have already some idea about the dependency structure, because you have to implement the reference distribution lambda hat on that assumption. So if you know that there is volatility clustering, for instance, going on, you have to choose already in the first step the corresponding reference distribution that accounts for that issue. And also in the resampling scheme, you have to account for that issue as well. You have to choose a residual resampling scheme that accounts for, in this case, for volatility clustering. And one example that we have discussed was the Rademacher distribution, but there are also other so-called PIC distributions. Yeah, and if we assume, or if we think that there's some sort of autocorrelation in the data, we have to choose a different lambda hat as reference distribution, and then we have also to account for a different resampling scheme. This approach is much more general, because it's based upon different assumption, namely that the point estimator beta hat is on expectation, that it's unbiased, that is on expectation beta. Yeah. So, and our resampling scheme accounts for both. It accounts for autocorrelation. It accounts for volatility clustering. Yeah. It accounts for any. If you choose a very large, or not very large, let's say 10% of the sample size. This is what we have done in our paper that we will discuss very soon. So we chose 10% of the sample size as the expected block length. Yeah? So obviously this gives us many dependency structures that we can account for when we do our resampling here. Yeah? So if you choose an appropriate expected block length, you can account for many possible candidates of dependency structures in the data. This is a non-parametric approach, like the previously discussed bootstrapping methodology, but it's much more general. It's much more general, but it works out very, very well. The only issue that you have to think about is the expected block length. Which block length should you choose? And that's usually the, let's say, problem when it comes to blocks bootstrap. This methodology is called blocks bootstrap. It's one type of blocks bootstrap. And what I recommend usually for empirical work is that you just try different block lengths. Yeah. So if your sample size is, let's say, 200 and you have an expected block length of 20, then try also 15 and 25, and you will be fine. Because if all of your T statistics and your lambdas, your lambda star, all of them show significance, then you can be secure that your results are fine. So the only drawback, obviously, is that we have to, which you already mentioned, that the kurtosis must exist. So if you read the literature on bootstrapping, they usually use T distributions with 5 degrees of freedom, and that's a good reason for that. Because if you use a T distribution of 4 degrees of freedom or 3 degrees of freedom, obviously the kurtosis doesn't exist. And then, even though you would get in sample a finite covariance matrix, you cannot employ any resampling here, because this guy will not converge. That is the problem. So you can apply bootstrapping. This bootstrapping scheme is very general and very nice, and you can have any dependency structure in the data, basically. But you have to ensure that the kurtosis of your data series exist. What we will do next is we will now have a look on the computer program, on the code, how to implement this code in a program such as MATLAB. This code is titled Blocks Bootstrap in Single Equation Models, and it covers exactly what we just spoke about here on the whiteboard. So the first thing that you have to do is here we have to load the vector of dependent variables, the y vector, and the matrix, the regressor matrix, denoted here as x1. So that's what we do. So the first step is to estimate the model. So we estimate the model via OLS and store the parameter vectors in a matrix which is denoted here as capital B underscore hat. First of all, we have to define the number of time series observations, which is our capital T. Capital T is the length of our data vector y, which is the vector of that gives us the dependent variable vector, and it's here obviously a capital Y, and N1 is the number of dependent variables. Obviously, we can bootstrap also if we have many dependent variables, or if we have that we basically use then for model a system of equations. So it's the same methodology basically. But in our case, we have a single equation model, so we have only one vector of dependent variable. So K is 4. We know we have here obviously 4 parameters to estimate. So that's why our capital K denotes the number of parameters, which is 4. So we have here draw 75. So our small n. You might remember we are talking about that. So we have small n is 75. So we have 75 draws. That we have with the expected block length. So in this notation here in the code, small n is 200, and this is basically so many trials we allow for generating blocks. So that's basically obviously if we have the geometric distribution, you might remember, we need so and so many trials. If we have an expected block length of 10, it could be that we have to have, let's say, 7 trials, 0, 0, 0, 0, 0, 0, 0, one more 0 and then 1. So that's then, this means we had 7 failures until success occurs, right? But it could also be that we have, 20 failures until success occurs. So the longer the expected block length that we have, so the longer needs this small n to be, because this defines in this code the vector basically go from trial to trial, where we investigate, okay, how many trials did we actually need in order to come up with the success, and knowing that, then we know also the what is the expected block length, because the expected block length in this case would be 7, right? So that's basically the way how it is. So what has been our n? It's now obviously denoted in the code as draws. So that's our draws. And if our expected block length is 10, and we choose the corresponding p, yeah, for setting up our geometric distribution, then obviously on expectation, yeah, we would have a 750, so it's draws times the expected block length. 750 would be the length of our simulated data matrix. Yeah, quite obvious. So then, obviously, let's say we want to have a block length of 10, because we had it also here on the whiteboard in our discussion. So then the corresponding, you might remember the how we derived, how we came from the block length for the probability of the geometric distribution. So the probability, if we desire block length of 10, the corresponding probability is 0.0909. Quite simple. So we also say here in the code, okay, we want to have a maximum block length of 25. Yeah, that's of course optional, but you can always wonder, okay, does it make sense if you have very, very large blocks in your synthetic data? Probably not. So I restricted this code to have a maximum block length of 25 because I said, okay, there's no dependency structure that is longer than 25 time series observations. So again, what happens in here? Obviously, we have here this, we determine our W matrix. Yeah, and here it is coded in the other way around. I have first the regressor matrix and then the vector of dependent variable vector. So then again, I have here 1,000, capital B 1,000, so we run 1,000 replications. Here in capital B1 underscore het, so we create a zero matrix that has 1 times k, so it has, its k is 4 and is 1, so it's a 4 by B, it's a 4 times 4 by 1,000 matrix that we store in each run. You remember that we just discussed that we store in each run the corresponding estimated beta vector using our artificial or our synthetic data. Yeah? So we have our beta hat 1, beta hat 2, beta hat 3, until beta hat capital B. Yeah? So that's every beta hat has a dimension 4 by 1. So the whole matrix here needs to be 4 by B. Yeah? And this is exactly what we code here in that code. Yeah? So in each iteration, small b, we store the corresponding estimated parameter vector in that zero matrix. So what happens here? So obviously, yeah, here we create a matrix, and this is overwritten after each run B. Yeah, after each run B, this guy here is overwritten. Yeah, we have to remember that as well. Yeah, it's probably not that important information, anyways. So when we do something here, yeah, the inner for loop here goes from 1 to draws, and if you push this button here, MATLAB tells us, okay, this for loop here ends in line 63. It starts here in line 32 and it ends in line 63. So what do we do? So we have obviously here in each run, yeah, in each run we create the corresponding data set that we need for each run's parameter estimator. Yeah. So we do something from 1 to draw, so we have 75 draws, you remember that. And what do? Okay, we construct a vector C0, and that has a dimension 200 by 1. So we allow for maximum 200 trials, yeah, using the geometric distribution, but probably we don't need so much. But this is obviously we have to choose a vector that has a large dimension, just in case we need a lot of trials until success occurs. Yeah, obviously it's very unlikely if we have a block length of 10 that we need 200 trials. It's very, very unlikely. Yeah. But just to ensure, if we have a long block length, if the block length is 100, yeah, then obviously it's more likely that we reach that limit. Yeah, but the question arises: so do you have to adjust? Obviously, this code needs to be adjusted. If you want to run this code for long block lengths, then obviously you might need some larger number here. But you will recognize if MATLAB spits you out in an error, then you might know that you have to do something different. But here it could be an error, for instance, if your if your block length is too large. Yeah, but well. So what do we do here for each draw? So also obviously, first we create this guy here, and this is also overwritten for each draw. Yeah, so we do 75 draws, and in each draw, yeah, we ask, yeah, for the number, let's say, of failures until success occurs. So that's basically how the idea is. So here, first we construct a zero vector. This is a 200 by 1 vector, and then we do something 200 times. And what do we do? So it says here, yeah, we draw a random number between 0 and 1, knowing that P is the probability of success. So this C1, using this function here, it is 0 if it's not smaller than P, if it's a failure. If it's a failure, it is 0 and a 1 otherwise. But we are interested in the failures, right? So if this guy here, if this is equal to 0, so if it's a failure, then we plug in our zero vector. Let's just take this away here. So our C0 is a vector of zeros, yeah, with 200 zero entries. Yeah. So now we use this random number generator. If this gives us a 0, we know it's a failure, and we want to have here then a 1. Then we go back to this loop here. Then in the next iteration, I is 2. We do the same thing. We employ the random number generator. If this gives us a 0, we know it's a failure, and we would put in here a 1. We do this until C1 is equal to 1. And then we break this loop, because we know then if success has occurred. So we have to end this if loop as well, yeah, and we have to end this loop where we generate the number of trials until success occurs, yeah, using the geometric distribution and the predetermined probability of 0.0909. Okay. So we take then the sum of this vector here. We just take the number of ones, because we know the number of ones. This is our failures, and this should be then the corresponding block length that we use for the first draw, right? So what happens then here? We say, okay, we code a number C4, and it should be the minimum of C2, and let's say our random number generator and our loop gives us, okay, we have, let's say, 7. Our block length should be 7, because we had 7 failures until success occurred. So our block length should be 7. So this guy tells us, okay, take the minimum of the number of failures that occurred, which is 7, or the maximum block length. And we know the maximum block length, we said, should be 25. So just in case, if we would have gotten here, if our code here, if this loop would have given us, let's say, 30 failures until success occurred, we would go with 25, yeah, because this ensures that we take that the maximum block length is the value that is, should be the largest value that we account for. Yeah. So this is basically what we code here. So the question arises: so how many overlapping blocks we have from our original data vector? And this is basically what comes here. Yeah. So we have t minus, let's say, if C4 is 7, so we have t minus 7 plus 1. So if t is 100 and C4 is 7, so it's 100 minus 7, which is 93, plus 1 is 94. So that's basically then the number of overlapping blocks, where we then randomly choose our block. Yeah. And that is what comes here then. So we create an indicating vector of possible block positions. Yeah? Because we have, obviously capital T. And here, let's say here is T minus C4 plus 1. So we know we have so and so many possibilities, yeah, where we can choose the block length from. Yeah? Overlapping blocks. So we have to now to draw randomly this block length of C4 that we determined here, and which is C4, randomly from our remaining overlapping blocks. Yeah? This is what happens here. So many positions do we have, yeah? And then we have to determine, okay, give me a random number, yeah, that is here on that interval here. Let's say the random number generator gives us the value here. So it means give me a block in our matrix W that has the block length of C4 and that starts here at this position. Yeah. So take this block out of that matrix, yeah, and construct a new matrix which is our WB. Yeah. This is what it does. So this is what happens here. Yeah? Yeah? Again, our W underscore boot, that is 0. Yeah? And this is basically how MATLAB works. Okay, it says, okay, put in this empty matrix there, and then add this block. Yeah? So we go to the position C7, and from C7 until C7 plus C4 minus 1, take all rows, yeah? And this double point here means take all columns. Yeah? So we grab the whole block out of that matrix and put it into the matrix W underscore boot. So then here is line 63. Here the draw loops ends. That means, okay, if we have done this 75 times, we have a very long new data matrix, W underscore B, which is much longer than we need. Okay, so that is usually how it works. And now we have to cut the observations that exceed T, that we don't need. We cut them away. This is what happens here. It says, okay, give me from the matrix W underscore boot the observations, the rows from 1 to T, so the first capital T observations and all columns. And that's then my matrix B, W underscore boot 1. This is how I denoted it here. Then we know, okay, we construct now the regressor matrix, and we know that in the matrix W underscore boot 1, we know that in the columns 1 to 3 are the original, or they are in this case our synthetic regressors, right? They are the bootstrapped regressors. So grab these guys, and put a matrix and put a vector of 1s in it as well. So what we get is our C2, which is our regressor matrix for the first run, yeah, using synthetic data. Yeah. So again, we have here in the first And the first column vector is a vector of 1 in the regressor matrix, denoted now as x2, and the regressors, and then we stuck in the x regressors, yeah, which are in the position in the column 1 to 3 of our matrix W underscore boot 1. You just have to remember how we have coded it. Yeah? We did it on the whiteboard the other way around, but it doesn't matter. You just have to remember how you coded it. Yeah? Where to find your regressors and where to find the dependent variable. Then obviously we know that the fourth vector of W underscore boot 1, there we have the dependent variable, our y. Okay, so we denote our y2, which is now based upon synthetic data. And once we have defined that, we can code our point estimator, yeah, using the synthetic data, yeah, which is then x2 transpose x2 inverted times x2 transpose times y2. Very simple. So what we do then is, okay, we take this point estimator and we put it into this matrix, capital B1 underscore head. And we put it into small b is 1, is the first iteration. So we put it into the first column. Yeah? Double point means put it into all columns. And we know already that we have 4, that this is a 4 by 1000 or 4 by capital B matrix. Yeah? And we know also that our beta head, yeah, for each run has a dimension 4 by 1. So obviously the dimension matches. So the first column is now ready, and then we go back. What this code will do then is, obviously, we will jump back to the beginning, and then our small b is then 2. Yeah? So we do this capital B times, so we get, if capital B is 1000, which we have chosen, we get 1000 different estimators. Okay? So then we have to construct the asymptotic sample, or we have the asymptotic covariance matrix based upon our synthetic samples. So first of all, we compound the, you might now remember, let's take this away. So you might now remember that we have in our beta 1 underscore head matrix, we have stored for each run the corresponding point estimators. Yeah. We remember here we had the alphas. Here we have capital B, and here is the first run. Yeah, then we had our beta 1. And of course, all of these are estimates. Yeah, so we have to put a head on it. And then we had here also the beta 3. Yeah. Beta head 3. So what we have to do here is basically we just take the sample, we take the mean. Yeah? So this is what happens here in this code here. Yeah, we do this for from J2 is running from 1 to K. So we do this for each row here. Yeah, K is obviously the dimension of the parameters. So we do this 4 times. So we take just the sample average. Yeah, which is basically the alpha head bar. We get the beta 1 head bar, beta 2 head bar, and beta 3 head bar. Yeah? Based upon the bootstrapped estimates. Yeah? So this is what we need. Basically, we need this for estimating the covariance matrix. So what's going on here in this code? So we first define a matrix of zeros, which has a dimension k by k, because our covariance matrix obviously needs to have the dimension k by k. Yeah. So again, we start with we say, okay, we define a matrix CC. Yeah. And what should it be? It takes now the first. It says, okay, for b is 1 until capital B. So we do something capital B times. So take, if let's say small b is 1, what should we do? Okay, we take the first, grab the first guy, yeah, which is the first estimator, yeah, using the first synthetic data sample. Take the first guy, subtract the vector of sample averages, yeah, and multiply it with itself transposed, right? This is what happens here. Yeah? So take that vector, subtract the vector of sample averages, and multiply it with itself transposed. So, and what's that? That's nothing else but the formula. You might remember that the expectation from beta hat minus the expectation from beta hat times beta hat minus the expectation from beta hat transposed, and that's the definition of the covariance matrix. Yeah? So we do this operation, but we do it for each vector here. Yeah? We take this guy minus this guy here, minus the sample average versus this guy here, multiply it with itself transposed. And what we get is the covariance matrix for the first iteration. Yeah? So what we do is then, yeah, our covariance matrix underscore boot is then simply this guy here plus this guy here. And we know this guy here is just zeros in the beginning. But after the first iteration, we add to the zero matrix this guy here. Yeah? The covariance matrix for the first iteration, yeah? If B is 1. So we do this also for all the other ones. Yeah? So we add this in this for loop here, basically, we add all of them, yeah, together in a huge matrix. So the matrix increases. This matrix becomes bigger as we go from B is 1 until B is capital B. Yeah, so the matrix becomes bigger and bigger because we always add, yeah, in each iteration the corresponding covariance matrix. Yeah, so this is what happens here. So that's the covariance matrix across all combinations. So what we do have to do then is, so obviously, yeah, we have to divide this guy, our big covariance matrix, by capital B. And this is what happens here. Yeah. In this case, it's not by capital T, it's by capital B. Yeah, because we have capital B simulated samples. So this is what is happening here. So and what happens then is, so what we do then here is in the rest of the code. So now we have constructed. This is the last basically line here. We have constructed what we wanted to do, which is our C hat. Yeah, you remember from our lecture on the whiteboard. This was the C hat. That we are interested in, and this is exactly what we have gotten here now in this code. So this is basically what's happening here, and now what we would like to do next is just as an empirical example. So we want to estimate, want to see how would we estimate then the T statistics. Yeah. So first of all, now let's upload some real-life data, and we have used this data set before when we have been talking about principal component analysis in this course. So let's define our y vector and our matrix X. Let's do the bootstrapping, and then we compound the T statistic, the bootstrap T statistics, and we compare it then with the standard T statistic. So that's basically what the code here would do is it would spit us out the point estimator using the actual data, which is here. Yeah, you might remember our actual data is x1 and capital Y. Yeah. Then we have to add, of course, if we want to do OLS regression, we have to add a vector of 1s here in our regressor matrix. We define it then as x11, and then we perform our OLS estimation, yeah, using that regressor matrix. And what we get, and then what we do then is, okay, we, as we discussed on the whiteboard, we grab each element, yeah, from this point estimator B, denoted here as B, using the actual data, and divide it by the square root of the corresponding element on the main diagonal of our bootstrapped covariance matrix, denoted here as covariance underscore matrix underscore boot1. That's what happens here in this code. And let's now do that. Let's open MATLAB, which we have here. Yeah, let's import some data. We have the data earnings rated anomalies. So let's. So what we have here is, let's see that we get it right. Let's do it one more time. Sometimes MATLAB needs a second trial. So again, let's open that file. This is our import wizard. We do not need the first vector because it gives us the date. Yeah? But what we have is the asset turnover in the first column, column B, gross margin, and in the third column we have the return on book equity, then we have return on assets, and we have the unexpected earnings surprise. Yeah? So we have 5 different asset pricing anomalies. So let's import the whole matrix into MATLAB. So we have it now here. Let's denote this as, let's call it XX. Okay. So let's define first what do we need for the code. Let's see. So we need, first of all, we have to define what should be our independent variable. Let's say we want the unexpected earnings to be our dependent variable. So let's code it as y. Capital Y is equal with XX, and we take it's the 5th column, right? So double point, comma 5, it gives us the, and if we now take plot Y, it should give us the plot of our dependent variable. Yeah, that's it. So that's how it is, and we have 486 observations, time series observations. So again, now we have to code also the y1, the x1, right? We have to upload exactly the x1, which should be our regressor matrix. Yeah, and we say, okay, we have the first 4 variables. Yeah, let's say, or let's take the first 3 variables as our independent variables. Yeah? They should explain the unexpected earnings surprise. So let's say our x1 is then defined as take the rows, take all rows and columns 1 until 3. Yeah. So that's now here, as you see here. If we do double click here, we can see it also here in our history here, in our where we have basically where MATLAB gives us the corresponding data matrix. So we have now defined our regressor matrix x1 and the vector of the dependent variable vector y. So now we just have to copy the code. That's basically how it works. We can copy everything until here. And of course, I will put you the code into Moodle as well, yeah, so that you can play around with it. Copy that into MATLAB, push the enter button, and then MATLAB does the rest of the job. So now we can basically, now everything is stored here in the workspace. Yeah. So now let's see how we have to continue estimating the corresponding T statistics. Yeah, our bootstrapped T statistics. So this is basically what we have just talked about. Just copy that into the command window and paste it in, and then we get the corresponding T statistics. So now we can we have to copy that and paste it in here, and then MATLAB spits us out the corresponding T statistics. So we know now the alpha, the intercept, the regression intercept, yeah, which is the corresponding parameter estimate for the vector of ones. Now remember our model is 3.48. Yeah? That's the bootstrapped T statistic, yeah? Using a block length of 10. Then the second parameter is minus 1.46. Yeah? And now we have to, because this is the correct, that's the correct bootstrapped covariance matrix, so we have to compare these values here with the standard T statistic. Because law of large numbers and asymptotic theory. So this is basically why we have done that, so that we can employ this law of large numbers. So then the point estimate, our beta 2, which is the point estimate for the second regressor, is minus 2.76, which indicates significance on a 1% level, right? And the last one has an exposure or a point estimate of 5.77, which also indicates significance on any level. So if we now compare this with the T statistics, that is a researcher would provide you that does not employ this bootstrapping reasoning, but that relies on the standard T statistics. And we know the formula already, we talked about it many times. Yeah. So we know from the previous step, yeah, the OLS, the standard OLS estimator is given by B. Yeah. And we know B is unbiased. Okay? We can always use B, the point estimator, because the point estimator, as long as the expectation, as long as the regressor matrix and error term are uncorrelated, beta is unbiased. So we can always use B here. So we know we get the regression residuals for the standard OLS regression of, but what do we have to do? We have to subtract from our Y vector the regressor matrix times the point estimator. This is what happens here. We get the residuals of our standard OLS framework, that we have spoke about in the first lecture, in the beginning of the first lecture. And now we remember that we, let's take this away. So we remember that the covariance matrix, of our beta hat, of our OLS estimator, is given by sigma square times x transpose x inverted. Yeah, that's what what researchers are usually doing. Yeah, they use the wrong T statistic, so they use the T statistic based upon the standard OLS assumptions. Yeah, now you might remember that we have supposed to estimate this by U hat transposed times U hat divided by the number of observations minus k. So this is exactly what happens here. Yeah. So we have to get the residual variance, sigma square. This is what we estimate here. Yeah. Then we can estimate the standard covariance matrix of beta, which is sigma square times the residual variance times the regressor matrix transpose times itself inverted. Yeah. So then we get here the standard T statistic, yeah, by simply grabbing each element from the point estimator like we did before, but now we divide it by this standard covariance matrix. Yeah? Again, we take the square root of the corresponding element on the main diagonal, yeah, which is, we have done this many times. So let's copy this part of the code and put it into MATLAB and push the enter button. And now copy this again, because we want now to see what it is. And this is what comes out. So first of all, what we see is if we now compare these results with our previous estimates, let's just take them, get them one more time, and put it here into the workspace just for comparison reasons. So we see that the intercept term, the T statistic is pretty much similar. Yeah? So they are pretty much the same. So our error does not concern the point estimate of the intercept term, but the other terms, obviously, we have a huge bias here. Yeah? We have a huge bias. So if we use standard T statistics, we would obviously we would come to the conclusion that the first regressor has a significantly negative impact, yeah, on our dependent variable, because the standard T statistic is minus 2.77, which indicates statistical significance on any level. Using the bootstrap counterpart that accounts for the unknown dependency structure, we would come to the conclusion that there's no effect. It's insignificant. Also, the exposure against the second regressor. Yeah? Using standard T statistics, we have a T statistic of minus 3.38, yeah? which suggests significance on any level. But using here the bootstrap counterpart, we see that it's actually slightly lower. Yeah? It's still significant, but the significance is overstated using standard T statistics. And the same is, which is probably most impactful, is the third point estimator. So we have the T statistic for the third point estimator, which is using standard T statistics. It is 14.08. Yeah, it is huge. But using bootstrapped T statistics, we see it's much lower. It's hugely overstated. Yeah, using bootstrapped T statistics, we see that the T statistic, the bootstrap T statistic, is 5.77. It's of course significant, but its significance it's much lower. So that's basically what we have learned from this exercise. Yeah. So using bootstrapped T statistics changes the statistical significance, and what we see here is the impact is severe, and this is exactly also what the simulation study in the Bootstrap, in the book from Leslie Godfrey, has shown, yeah, that basically using standard T statistics, they overstate the significance. Yeah? So we would think that some associations, some links in social science are significant, even though they're not. And that might be one reason for why so many scientific studies fail replication. Yeah? Because probably they use the wrong statistics. Yeah. So, and just to come to show you the scientific paper that I have been talking about. So let's go back here. Let's close MATLAB. And let's go to the so let's go to my the desktop here. published papers. And now we have to go to the recently published paper of mine, and that's the paper that I've been talking about. Yeah, so that's the paper entitled Speculation and Lottery-like Demand in Cryptocurrency Markets. So, and if you read this paper, so just in case if you want to use this test statistics in your own research, of course you're welcome to do that, and probably you should do that. It's proposed here in this scientific paper published in the Journal of International Financial Markets, Institutions and Money. So my co-author, Juha Juntila from the University of Jyväskylä, where I'm also affiliated with that university. Juha is a professor there in economics, teaching econometrics, and I am adjunct professor of economics at the same school. So, and what we have done here is we have basically proposed this test, this blocks bootstrapping test for cryptocurrency markets, and we have argued that this market obviously has many dependency structures. Yeah, there are some papers they report regime switch, they report speculative bubbles, autocorrelation, volatility clustering, everything. Yeah, so you see many problems here in this market. So we need a robust T statistic. And here's basically how it looks like in this section here, where we basically talk about how to implement this test statistic. So you can see it here in this paper. It's published now online, and probably during this year 2021 it will be at some point pop up in one of the scientific journals. But here's basically the methodology described in detail. Yeah. So obviously academic people, they like to read more complicated things. So the way how I explained it to you is maybe a little bit more intuitively explained. And here in the scientific paper, you will see a little bit more complicated version, which is basically doing the same thing. But yeah, if you use this test, you can of course do that, and you can of course play around with it. You can change. You might remember if you change the block length. Yeah, you have to change the p. You have to compound. You have to just to compute what's the p, and you might have to do some changes if you have very long block lengths that you want to choose. Then you might change the length of the this vector C0, yeah, where you store the trials, yeah, for the geometric distribution, and you might change the n, small n, as well. But yeah, that will of course spit you out some errors if you run into troubles, and then you might consider what you have to change in that code. Yeah, this is what was the subject, or basically the content of this lecture series on problems with statistical tests and empirical work. I hope that you have understood the main problems here. Obviously, we have, as we told in the beginning of the lecture series, we have problems in social science research because people report published papers, and they have results that fail scientific replication. So we have seen that a recent study has shown that 80%, as much as 80% of scientific studies, they fail scientific replication. So they report there's something significant, even though it's not. And one of the problems might be that people use simply the wrong test statistics. Thank you for your attention.